She tied you to the kitchen chair. She broke your throat and she cut your heart. Can't go that high. And from your lips she drew the hallelujah, hallelujah. I love these singing intro video, or these singing video intros. So whenever I use not the microphone, the audio will just cut out at random times, like it did in that singing video. But when I sing into the microphone, it sounds like I'm eating it. It's so bad. It sounds like the beach. The wind. It's terrible. It was not pleasant to listen to. So, there you go. So, in geometry right now, we are learning some I'm here to teach you how factorials, permutations, and combinations work logically, how you can physically think about them versus just some random formula that they give you that's supposed to make sense, because Lord knows it does not help me at all. I don't know what the exclamation point means, so I'm here to teach you some stuff. You're about to learn some stuff today. Math addition. I'm not gonna copyright, but let's get those brain cows milked. Sorry, that was copywritten. So first, factorials, which is essentially you have a number and the symbol's an exclamation point behind it, which symbolizes that you multiply every preceding number after it by itself. So you multiply. If it's 5 exclamation point, you would say you multiply 5 times 4 times 3 times 2 times 1. And this is for real world examples such as lock combinations, when you have 26 numbers and you have a 5-digit lock combination, and it could be any of those, The logic behind this is how many ways can I arrange n distinct things in a sequence. So if you have 5 numbers, you can arrange it 1, 2, 3, 4, 5, and then you can, since there's 5 numbers, every way you arrange it, you see to me, so it goes like 1, 2, 3, 4, 5, 1, 3, 2, 4, 5, 1, 4, 3. There's 5 ways you can arrange the first number, and then 4 ways you can arrange the next number, then 3 ways you arrange the next number in that specific pattern. Factorials are the easy part of this. Permutations and combinations are, let's do a vocab word today. Today we're going to start off with not a very sophisticated word, but it's paradox. It's a noun, and it means a statement that contradicts itself but may be true. So think oxymoron, or what's that other word? I don't know, but it contradicts itself, but that doesn't mean it can't work. I'll find an example. So another definition is a statement or concept that seems self-contradictory or logically unacceptable, yet might possess an underlying truth. It often highlights inconsistencies within accepted beliefs, revealing that our understanding of reality is incomplete or nuanced. And some main examples are the liar paradox, which is this statement is false. If this statement is true, then it must be false as stated. Oh, so if the statement is this statement is false, and if that statement is true, then it must be false as stated. But if it's false, that means it's true. So it's sentences that have the wording in them says one thing, but the actual action of the sentence reveals another thing. The next one is the Socrates paradox. If you remove 1 grain of sand from a heap, you still have a heap. If you keep removing single grains, when is it no longer a heap? So, some food for thought. Paradox. I'll try to use that. It's going to be hard to use, but I'm going to try to use it once in this video. Next is permutations, which is factorials with a few more steps. I'll explain it logically. Permutations are how many ways can I choose and arrange k items from n distinct items where order matters. The most common example and more problems of this is there are 7 runners running a race. How many different ways can the runners win first, second, and third place? So you gotta think of it like that. How many different ways can 7 people be arranged into a group of 3, but the order matters. So you'll have very large numbers. You'll have a very large number for the amount of combinations there can be. So the logic is you have n items, you're filling k ordered. Ordered is the main concept here. Ordered slots. So you may have seen the formula for this. The formula is whatever, you don't need to know that. I'm not explaining the formulas today, I'm just explaining how it logically works. The key idea is that in a set order, ABC and BAC, although like they're the same numbers, they're counted separately as 2 separate things because the order of the letters are not the same, so therefore they are not the same. Yeah. I don't know why I explained permutations first, because combinations is just permutations, but the order of the selected group does not matter. So a combination answer is how many ways can I choose k items from n where order does not matter. So 7 runners running a race, how many different ways can people finish in the top 3 places? Order does not matter. Everyone gets a gold for winning. Top 3, we'll say. So that's all it really is. And in this case, if you had letters A, B, C, D, ABC and BAC would be counted as the same because they have the same amount of letters, or the same letters in that 3 period. Because it's like if you had a bunch of fish and you just grabbed 3 fish. It doesn't matter which fish they are. If you grab, I don't know where I'm going with this, honestly. The runner analogy is much better. But the key idea here is that ABC is the same committee regardless of the order. On to the relationship. So factorials, the formula is just n exclamation point, n being number. And it's all it is arranging all of the n items. How many times you can arrange n items? You use all of them. You use all of the things given. You can see how many times they can be rearranged. For combinations, you have a set group of things and you see how many different combinations you can find for a sample group. How many? So no picking k from it. Factorials count all arrangements. Permutations restrict to k slots. Combinations remove the overcounting from ordering. Let me know if you don't understand, because I understand now, but if you don't, let me know.